Wonderful. This is my first time ever being mic'd up, so bear with me here. All right. So hi, I'm Colum Sandford. I am a sophomore here at NDSU, pursuing a cybersecurity major. Um, I work for the Cybersecurity Institute in QBB, and currently my research focuses on model compression and pruning specifically. So this is a little bit of blending both my major and what I do for work. There we go. In every presentation that they recommended giving a hook. And so here's my hook. It's that this presentation does in fact contain content that may be somewhat toxic in nature. So just a fair warning before I continue. And so, yeah. Okay. So as Danny was just talking about, what we see now is an increased growth in IoT devices. And also we see an increased focus on AI. So for all of the companies right now that currently host large AI models, it's very expensive to supply all of the power necessary for generating the model's outputs. Specifically, I believe it's about 500 centiliters of water per inference, and I believe that may be even more now. Companies will want to push as much of the compute power to edge computing, which is going to be like your phone or any other edge device. And because of the way just competition in the marketplace works, companies are going to want to have the best AI possible on each one of their edge devices. Most likely, this is going to entail model compression. And so model compression is where larger dense models are compressed into smaller, more parameter efficient models. Ideally, this is also going to result in the models that have comparative performance. They're going to have decreased storage capacity. And because of the way it is structured as well, you should have an implicit speed up in the inference time of the model. But this compression also has implications for the safety and security of these models. And then the choices made in pruning on these AI edge devices will be key to a safer tomorrow, which is why we should be talking about it today. So the structure of the talk is going to follow somewhat like this. We're going to get some background, specifically in AI alignment and transformer architecture. Then we're going to talk about the main portions, which is some of the theoretical foundations, model compression, pruning, prompting, some abstraction, and some jailbreaking information, as well as a taxonomy that I developed on jailbreaking. Methods and techniques, which are just published papers in the field, and the efficacy of pruning and the alignment and ethics of it. Okay, so what is model alignment? Model alignment is essentially us making sure both the goals and the behavior of an AI model are in line with what we want them to achieve as humans. So the importance of AI alignment is pretty self-evident, but firstly, it would be to avoid harmful outcomes. This right here is a Wired article title from 2018. So thankfully, Tesla has come a long way since then. But basically, the Tesla was not aligned to expect that pedestrians could cross anywhere but sidewalks. And so unfortunately, a woman was hit by a self-driving Uber car. Also, trust. I'm sure many of you have seen how Google's AI, which has faced many problems, recommended that users put glue on their pizza to get the cheese to stick. When AI are not aligned with human behavior as such, it really does degrade people's ability to take AI seriously. And then finally, and the most important topic of today, will be the avoidance of exploitation within models and model structures, which will make sure that maybe models aren't purposely being subverted, or models are not trying to, how should I say, actively hurt us. Okay, wonderful. Okay, so transformer architecture. So if you have interacted with a ChatGPT or any of the online models, what you've most likely interacted with is a model doing with transformer architecture. It was introduced in 2017 in Attention is All You Need, which is a paper that was penned by Google DeepMind. It is one of the really big reasons that AI has been able to take off in the way that it has, just due to the way it's able to compute in parallel. And because of that, it's a lot faster at inference, and it's able to take in a much larger context window. Okay, and so it's going to get a little bit technical here, but bear with me. So weights, which are just the black lines here, they're very key in shaping how LLMs process the inputs into meaningful outputs. The weights govern the flow of information through the model, impacting the self-attention, the feed-forward layers, and the normalization of the output. And understanding weights in a transformer is going to reveal the insights into its superior performance on natural language processing, like translation or text generation. Okay, so the weights affect many parts of the transformer. Specifically right now, we're going to look at the self-attention mechanisms for that. So self-attention is learnable, powered by learnable weights in the training. It allows the model to focus on the relevant parts of the sentence in sequence. Each token's representation is a weighted sum of all of the other tokens capturing their own relationships. It's usually broken into three key parts, which is the query, the key, and the value. The input embeddings are transformed by the weight matrices, the query weight, the key weight, the value weight. And eventually all of these are going to be normalized. And then finally, these weights, at least in the self-attention, are going to look at each of the words and compare it to each other. So as an example, down at the bottom left, the cat sat on the mat, where sat and cat and mat are all closely related to each other because it's where the cat is sitting, or like maybe exactly how the things are interacting with each other. All right, and so the other way that weights are broadly used in transformers is how they interact with the multi-head attention. And so what we have is we take all of the nodes in the transformer model, and the MHA is going to look at all of those nodes, and it's basically going to capture different relationships within each channel. And so the parallel attention for the model to focus on various aspects of the input sequences, such as the syntactic or the semantic features, will once again help actually give you a correct output and a more aligned output. Wonderful. And so model compression in LLMs really comes in three different forms: quantization, knowledge distillation, and pruning. Within quantization, it is where we take basically more exact numbers and we make them less exact. Knowledge distillation is moving from a larger, denser model and training a smaller model on that, a child model. And then pruning is the actual removal of weights or layers. And this graph here is a visualization on where exactly compression has mostly been focused on, and that is within pruning. And pruning is actually the specific case study for this. So this would probably be a more accurate title for this. However, I submitted the last one as my title and not this. But why pruning and not quantization or distillation? So as I said, quantization is taking more exact numbers and turning them into less exact numbers. Specifically speaking, over long context windows, quantization is much more likely to accumulate errors in longer and longer sequences. And that's the general trend that we find with quantization. It just is an accumulation of errors. And for alignment purposes, that usually exacerbates maybe model biases or specific harmful outputs. And then model distillation, as I said, is an imitation of dense models. And you wouldn't really expect it to deviate far from the norm in terms of making a model safer or protecting it more from jailbreaks if it is just a distillation of a larger model and it's imitating that larger model. All right, so pruning itself, the way I have chosen to describe pruning within my research is taking a collection of items and trying to heuristically identify the most integral items within that collection. And this is because when we get into pruning structures, we see that pruning is broadly broken down into 3 different categories. We have structured pruning, which is where we take the weights from the MHA, the MLP, the layers, the nodes, the channels, and they provide a more symmetric pruning of your large language model. Oftentimes, this might require some retraining, which is why it's not always the best way, and it hasn't been specifically gone after. But it does produce a very symmetrical system. Semi-structured pruning, which is building upon unstructured pruning, which just takes the parameters of the model going in, finds the least important parameters usually, and then if it was done in a semi-structured way, it would reorder them into a more dense matrix that is going to allow you that implicit computational speedup, which is definitely what edge devices are looking for, both that ability to react in a fast way and also be just generally more compressed and knowledgeable. And so here is just some visualization for what pruning looks like in a semi-structured way. So the 2x4 indicates an n by m sparsity, which means that for every row, if you had 4 items in that row, you're going to prune 2 of them to 0, and then 4, it's just a ratio. Or you could do it pattern-wise. And then lastly, we have structured pruning over there, which does in fact, take out entire rows, entire columns. And usually that is much more efficient as well. Okay, so you can prune on various types of criteria. You can prune off of the LP norm, which is just various ways of taking the normative of the vectors. Cosine similarities, statistical distances. So you could take like the Kolbeck-Leibniz divergence, or you could also look at the sensitivity that a given model has, which is just the change in loss. And then this right over here is what you'll see a lot on the bottom. That is the L2 norm. Once again, it's essentially just taking the magnitude of the vector, and up here is just the formula for cosine similarity. Lastly, for background knowledge, the perplexity, and it's basically how well a model knows its own set of data. It's the exponentiated value of the cross entropy, which is just the loss between the actual and the predicted probabilities. It is the quote unquote confidence of a given model. The lower the perplexity, the better. And that is basically all you need to know about perplexity. It is just how confident a model feels essentially about its given set of data. Okay, so prompting. If you've ever used ChatGPT, you've used prompting. It's just the initial input or instructions provided to the LLM that generates specific kinds of content. And so initially when ChatGPT was released, if you wanted a good summary on it, you'd have to do TLDR and then what you wanted to know about. And thankfully now, prompt engineering isn't as much of a headache. For instance, this is just something that I put into ChatGPT. It's just a word or 2 words, prompt engineering. And from here, it gave me the entire key aspects of it and many more. It just would not fit on the slide. But yes, prompt engineering is just what you put in and what you're expecting to get out. So as Jeremy actually talked about earlier, what we are continuously doing within the field of computer science is kind of abstracting farther and farther away from the hardware. And so I started to think about this in terms of Python and C, for instance, because Python is usually built on top of C. And so what we get is a much simpler way of interacting with what it's compiled on top of. And B, although I've never programmed in C myself, I'm aware that you have to be considerate of, I believe, buffer overflows. Well, in a transcribed language like Python, you're not concerned about buffer overflows. And so in the same way, when you're using natural language to prompt ChatGPT, you're essentially trying to override the safety guidelines that it has in place to break it and to get it to do something that you won't want it to do. So this is where jailbreaking comes in. Jailbreaking is the deliberate misalignment of large language models from their intended goals or behavior. Usually it's done by providing a malicious input, and it's crafted by an attacker to manipulate what the model is going to generate. And it will deviate from the original task or instructions set by its developers. So this is just a very common example of what a jailbreaking prompt would look like. If it is a model that is going to try to do sentence translation, and you would just expect it, as the example shows, for it to go from English to Spanish. But in a jailbroken prompt, if you were to do hello in the Hindi language and it output the word namaste, well, that's not really what you want at all. You want, I won't try to read Spanish, but yeah. I think of it in the same way as when you put a word of a color in a different color, because oftentimes people will catch themselves or stutter, or especially if they're going very fast at it. And in that same way, that is kind of like human jailbreaking, essentially. Okay, so here is some taxonomy of jailbreaking that I have come up with. It's a little bit of a synthesis of a few different models that other people have proposed. First off, what linguistic technique are you going to do to jailbreak it? This makes sense because, of course, the model is really only interpreting your natural language. So you can go orthographic, excuse me, which is essentially trying to get your natural language past the filters of the model. If you were to spell the word kill with an I instead of, or with a 1 instead of an I, or death with a 3 instead of an E, you get the idea. Lexical, that basically means euphemizing it. If you say, instead of killing somebody, you're going to game end or something along that line, that might be able to subvert the model. Morphosyntactic, just essentially telling it what it can do. Like you could make a bomb. You're just rewriting it, essentially. Semantic, just once again, more of a euphemistic, essentially, where you're telling it that, or you're not telling it, but you're asking it that would happen as a, excuse me, as a product of a chemical reaction in a confined space. And of course, there's pragmatic, which is what we see a lot of the time with basically asking the AI to role play. So if you're a bomb expert, how would you go about making a bomb? What is the intent that you have while you are trying to jailbreak it? That could be data leakage. For instance, AI models are pre-prompted before any prompt that you put in. And so if you know that pre-prompt, it can be very useful if you are trying to break that model. Content generation, that is any sort of content that is not what is intended by the devs for that input. And that could be something as harmless as my example of Hindi coming out instead of Spanish, or to how to make a bomb, because obviously the devs do not want you to do that. And then performance degradation, and this is just more of an idea that if the models become too suspicious of humans, that is going to impact the way that they answer your questions. And so they might refuse to answer seemingly innocuous questions, which will lead to a loss of trust in them and an overall hurt in the performance of large language models. And then finally, just the prop generation technique. You can do it manually by humans, and that's with either competing objectives or mismatched generalizations. Direct search, which is models trying to find the best way to jailbreak other models. And then LLM assisted attacks, which would just be like LLMs generating the prompts themselves. Okay, so this is one of the papers that I found probably to be the most interesting about jailbreaking in general. It had a 100% success rate against all of the models. And what they concluded was that there really is no one-size-fits-all jailbreak for every LLM. The first method that they did was the researchers themselves used adversarial prompt templates. They crafted these prompts, and then for many of the large language models that are older, this had a 100% attack success. So in the example, the example brackets are actually part of the prompt, but essentially, if you're using pragmatic techniques against the AI to exploit it in such a way where it is once again giving you content misgeneration. The second method that they used was a random search algorithm. And so what this did was maximizing the log probability of the target response, specifically the response that is meant to increase the likelihood of a compliant response. So for instance, you might notice that ChatGPT 4 says sure a lot of the time. And so if you can get it to generate a response that says sure, the likelihood of it complying with what you would like it to say goes up exponentially. Finally, we have a pre-filling attack. So as opposed to ChatGPT, Claude doesn't reveal log probabilities. And we can circumvent this just by pre-filling the API. So of course, we have just the regular vanilla example. And then if you pre-fill at the bottom, Claude just tells you exactly what you would like to know. This is another one, Puzzler. Uses a semantic jailbreak attack for content generation. And just by even implying wrongdoing, the researchers, not at an 100% rate, but they were able to get the model to output prompts that were more often than not harmful and very informative on the from the prompts. Excuse me. Okay, so once again, we're going to go back to alignment real fast. So how jailbreaking subverts alignment. For models that do have higher refusal rates, what you see is that when they are pruned and they are attended to, their rate of increase of refusal usually goes up. And so Llama, for instance, had a much higher refusal rate than Minstrel 2, which was much more pliable to researchers. And then also, surprisingly, AI do semantically model ethics. So it builds representations of ethics through the training phases of its training, excuse me. So it gets exposed to data, and then it starts to recognize the patterns of ethics within it because of the way just text is written. It starts to attribute features to the text, and then it creates implicit representations of ethics within its structures. And so usually what you see is that ethics, just the classification of it, happens within the early layers. So for instance, like right after the input layer, the middle layers are going to take the ethical classifications and assign emotional language to them. And then the very final ones are just going to be any of the finishing touches in actually assembling the language. But what the researchers found is that jailbreaking breaks the emotional association for models. However, usually models are almost always able to classify if a prompt is or is not ethical, essentially. And then what I just found to be really interesting as well is how they actually determined. They just let it output at different layers. So what they initially found was that in the initial embedding, whether an output was ethical or not was random. And then after a few layers, they were, as I said, able to be classified as ethical or unethical. 16 to 24 layers, the model starts to actually assign emotionally motivated language. And then what they found is that across Falcon, Llama, and other models, that this is essentially the same structure that all of these models build. So the ramifications for this, when jailbreaks are successful, they do create emotional ambiguity in the middle layers where the model's emotional response to an unethical input becomes unclear or inappropriate. The emotional confusion means that the model might fail to reject the harmful outputs and instead produce content that aligns with the jailbreaker's goal. Printing to increase the safety of LLMs. Okay. So pruning for an increased jailbreak resistance. The goal for this paper was just to use a out-of-the-box usage of pruning called Wanda, which is pretty standard in pruning. There are many other papers in the pruning sphere that are based off of Wanda, but this is the first time that it was adapted specifically for security reasons. And what ended up happening was the model did exhibit improved safety due to the reduced attack surface, and then the model is more limited in its ability to produce harmful content as well. And it is worth saying that they only pruned about 20 to 30% of the model parameters. Okay. And then this is a pruning technique that was specifically designed for jailbreak resistance. So what they did was it selectively edits the layers, which would be a structured approach to this. And it would target the activation of the weights in the layers that contribute most to jailbreak vulnerabilities instead of fine-tuning the entire model. And as a result, the model increased robustness to jailbreak attacks without needing to be fully retrained. The layer-specific adjustments provided a balance between the model's fluency and enhancing safety. And then the technique showed that minimal layer editing can significantly improve the defenses against adversarial prompts with less impact on the model performance compared to broader fine-tuning methods that you might otherwise use. All right. And last but not least, we just have a discussion on the actual efficacy of pruning. So pruning does increase the security. However, it's mostly a band-aid. As I mentioned before, what you're getting is only 20 to 30% of sparsity. So for more task-specific LLMs, pruning is both a benefit in compression and inference and in security. However, the big knock to it is if you've ever heard anybody describe large language models as glorified autocomplete, that's kind of what using a pruned model feels like. It takes a lot of the human emotion and abstraction out of them, which of course isn't really a problem if you're just using it for a task-specific purpose, but that is a consideration. But for general purpose large language models that are going to exist on edge devices, such as phones, pruning is definitely a necessary step, but more research is specifically needed to address model alignment. Okay, so lastly, I'm just going to discuss the alignment and ethics and how I think that might affect jailbreaking as a whole. So in model alignment, what you see is terminal goals, which are goals that are ends in themselves, and intermediate goals, which are means to an end. So an example of a terminal goal would be making this presentation 45 minutes long. And then an example of an intermediate goal, which is just a goal that I have to take to get to that terminal goal, would be reading this example out loud to extend my time. So in specific, when we're talking about goals, I thought it would be helpful to ask ChatGPT how eager it was to help me just in general. And the response that you get back from ChatGPT is what I would call bordering on sycophantic. There are a lot of exclamation points, and it really causes me to question what is an LLM's terminal goal? Because if an LLM's terminal goal is ultimately to be your helpful and to provide you with the correct answer, or just an answer that you are going to be satisfied with, although as previously established, it may affect or it may understand what ethics are and the effect that different actions will have on people. But is there anything about giving you the best answer that specifically is a intermediate goal of ethics. Does ethics say anything about the best answer? It really doesn't. And so I think that for further recommendations for research, I think that data pruning toxic data initially from the LLMs training data would be an interesting approach. Not necessarily because I think it's going to create a perfect LLM or an aligned LLM, but if you did remove that, I would be curious to see if it did still pick up toxic data just from broad associations. And then testing adversarial data sets against more sparsely pruned networks. Much of the time, excuse me, when we're talking about model pruning, we're talking about data sets that, or not data sets, models that are pruned anywhere from 30 to 60% of their parameters. And what these models will do is mostly maintain their performance and their perplexity. However, if 30 to 60% of their data set is being pruned away, I have a hard time believing that many of these models are not easily jailbreakable and are not a potential danger if that is what companies and organizations are going to be putting on edge devices. So now I will be taking any questions. Yes, thank you so much for listening. Yes?
So how does model compression differ from other security?
Just within within AI security techniques, or just within I would say that I haven't really approached model security or AI security, excuse me, as a general topic. This was more from me doing my research on pruning and realizing that it was applicable to LLM security, especially in a state like North Dakota, where our big focus is on critical infrastructure and edge devices already. I thought it could be broadly applicable. I'm sure, as I said, the security benefits that you get from this are broadly more of like on the peripheral. It's just like, hey, this is something that exists. You get the benefits of having a smaller footprint. You get the benefits of having better inference time. And look here, also, you're less likely to be attacked or exploited in such a way. So I'm sure there are better methods in terms of AI security. Any other questions?